Dear students, in the previous class, we have defined what is multicollinearity. We have also discussed what are the causes of multicollinearity. Today, we discuss what are the consequences of multicollinearity. We discuss the consequences in two heads. One is the theoretical consequences. The other one is the practical consequences. So first we discuss the theoretical consequences of multicollinearity. To explain this, we consider the three-variable model in deviation form. Ya is equal to x 2y plus beta 3 hat x 3y plus u hat. The three-variable model in deviation form. Now we assume that collinearity is perfect R between x2 and x3 is equal to 1. We assume that multicollinearity is perfect. Now the question is, what are the consequences? As we have discussed in the last class, if multicollinearity is perfect, OLS estimators are indeterminate. OLS estimators are indeterminate and their standard errors are infinite. Standard errors are infinite. That means OLS estimation is not possible. Let us explain this. We have derived the normal equations in deviation form earlier as sigma yi x2y is equal to beta 2 hat sigma x2y square plus beta 3 hat sigma x3y x2y sigma yi x3y is equal to beta 2 hat sigma x2y x3y plus beta 3 hat sigma x3y square. These are the normal equations in deviation form. From this, we have derived beta 2 hat, beta 1 hat, beta 2 hat and beta 3 hat. Now, beta 2 hat is equal to, in the denominator we have sigma x2y square into sigma x3y square minus sigma x2y x3y the whole square. In the numerator for beta 2 hat, sigma yi x2y into sigma x3y square minus sigma yi x3y into sigma x2y x3y. That is the expression for beta 2 hat. The expression for beta 3 hat is, the denominator is same, sigma x2y square into sigma x3y square minus sigma x2y x3y the whole square. In the numerator, sigma yi x3y into sigma x2y square minus sigma yi x2y sigma x3y x2 and beta 1 hat is equal to y bar minus beta 2 hat x bar 2 minus beta 3 hat x bar 3. And remember this, we have derived these values earlier. Now assume that x3i is equal to lambda x2i. x3i is equal to lambda x2i. So that in deviation form x3i is equal to lambda x2i. That is, x3i is a perfect linear combination of x2i. Now we substitute the values for beta 2 hat. That is, in the place of x3i, we substitute lambda x2i. Then beta 2 hat is equal to sigma yi x2i into sigma x3i is lambda x2i square minus sigma yi x3i is lambda x2i into sigma x2i lambda x3i divided by sigma x2i square into sigma lambda x2i the whole square minus sigma x2i lambda x2i the whole square. The values are substituted. Now you know that this term becomes lambda square, lambda into lambda square, sigma yi x2i, then sigma x2i square, sigma x2i lambda x2i, sigma x2i square, sigma x2i square into sigma x2i square, that is sigma x2i square, and lambda is taken out, then sigma x2i square into sigma x2i square, sigma x2i square all square. That will give you 0 by 0. That will give you 0 by 0. That means wireless estimation is not possible. That is, beta 2 hat is indeterminate. If you substitute the values in this equation also, you will get the same result. You will get the same result. Remember this. These two terms are equal. These two terms are also equal. Now, in matrix form, the x transpose x matrix for the 2-variable, 3-variable model in deviation form is sigma x2i square, sigma x3i x2i, then sigma x2i x3i, sigma x3i square in deviation form. Now if you substitute this relation, this becomes equal to sigma x2i square, then sigma x3i is equal to lambda x2i into x2i, lambda x2i square, sigma x2i into sigma x2i lambda x2i, sigma x2i lambda x2i, sigma lambda x3i, so lambda x2i the whole square. Now sigma x2i square, then this becomes sigma x2i lambda square into sigma x2i square all square minus lambda square into sigma x2i x2i, sigma x2i x2i, again sigma x2i square all square. And if you this is the matrix X transpose X. If you take the determinant of this, it becomes determinant of this quantity is lambda square into sigma x2y whole square minus lambda square into sigma x2y square whole square. Lambda square into sigma x2y square whole square minus lambda square into sigma x2y square whole square. So the determinant become 0. If the determinant of X transpose X matrix is 0, the inverse of X transpose X cannot be taken. That means the vector beta hat cannot be derived. So if multicollinearity is perfect, OLS estimators are indeterminate. OLS estimators are indeterminate. Now the question is, why we obtain such a result? That is, why we have the result that beta 2 hat is equal to 0 by 0? It's a very important question. Now the answer is, in terms of our definition, beta 2 hat measures the partial effect of x2 on y, keeping x3 constant. Similarly, beta 3 hat measures the partial effect of x3 on y, keeping x2 constant. But if x2 and x3 are collinear, we cannot keep x3 constant while estimating the effect of x2 on y, or x2 constant while estimating the effect of x3 on y. That means the separate effects cannot be determined. And beta 2 hat is the partial effect, the separate effect. So the separate effect is not, or the separate effect cannot be estimated if there is multi-collinearity, perfect collinearity between explanatory variables. To see this differently, consider this yi is equal to beta 2 hat x2y plus beta 3 hat lambda x2y plus u hat. We substitute x3y as equal to lambda x2y. This will give us beta 2 hat. This will give us beta 2 hat plus lambda beta 3 hat x2y plus u hat. That is yi. So we write it as yi is equal to alpha hat x2y plus u hat. Alpha hat x2y plus u hat I, where alpha hat is equal to beta 2 hat plus lambda beta 3 hat. Actually, in this specification, if there is a relation like this between x2 and x3, there is only one independent variable, not two. That independent variable is x2. If you apply OLS, you will get an estimate of alpha hat. And alpha hat is equal to beta 2 hat plus beta 3 hat. Mathematically, this is one equation in two unknowns. So unique estimates of beta 2 hat and beta 3 hat is not possible. One possible solution is you give values arbitrarily to beta hat 3, then you can estimate beta 2 hat and vice versa. The message is, in the multiple linear regression model, our aim is to estimate the partial effects, the effect of each independent variable on the dependent variable. But when there is high perfect collinearity, whenever one variable changes, the other also changes, so that we may not be able to estimate separately the partial effects. That is why we have we will get an equation 0 by 0 like this. So that is the first. OLS estimators are indeterminate. Now let us see what is the second. The second is their standard errors are infinite. We know that the standard error or the variance of beta 2 hat is the denominator, the same denominator sigma x2y square into sigma x3a square minus sigma x2y x3a the whole square into a sigma square here. Here it is sigma x3a square, variance of beta 2 hat. Similarly, variance of beta 3 hat is sigma x2y square by the same quantity into sigma square. These quantities were derived earlier. You just refresh your memory. Now, we have x3a is equal to lambda x2. So, we substitute the values is equal to sigma lambda x2y square divided by sigma x2y square into sigma lambda x2y square minus sigma x2y lambda x3y the whole square into sigma square. This becomes lambda square into sigma x2y square divided by sigma square is there, sigma x2y square into lambda square sigma x2y square minus lambda square into sigma x2y, this is lambda x2y, sigma x2y square whole square is equal to lambda square into sigma x2y square by 0 into sigma square. And this is equal to infinity unless the numerator is 0. Or unless we can say this is not equal to 0 unless sigma square is 0. And sigma square is the variance of u. There is no reason to believe that it will be equal to 0. So naturally, variance of beta 2 hat is infinite. So if multicollinearity is perfect, OLS estimators are indeterminate and their variances are infinite. You know, in terms of the matrix algebra, we know that variance of the vector beta hat is equal to sigma square into x transpose x inverse. In this matrix, the diagonal elements are the variances. So if there is high collinearity, the diagonal elements increases indefinitely. That is the problem. But as we have mentioned earlier, multicollinearity is used nowadays to represent perfect collinearity and also less than perfect collinearity. That is the situation in which R between x2 and x3 is 1 and also less than 1. As an example, suppose that x3a is equal to lambda x2y plus Va, where Va is a stochastic error type. In this case, if you substitute the value of x3a in the formula for beta 2 hat or beta 3 hat, you will not get the expression 0 by 0. You can estimate beta 2 hat, beta 3 hat and also beta 1 hat. Estimation is possible. So, unlike perfect multicollinearity, where estimation is not possible, in the case of less than perfect multicollinearity, estimation is possible. Now the question is, if estimation is possible, what is the problem if there is collinearity between explanatory variables? And remember this, in the regression analysis, in all the cases, there will be some collinearity between explanatory variables. If there is no collinearity between explanatory variables, we say that explanatory variables are orthogonal. Orthogonal regressors is an exception, not a rule. You will not get orthogonal regressors. In all the cases, there will be some collinearity. And the assumption of classical linear regression model is there should be no perfect collinearity between explanatory variables. So even if there is some collinearity between explanatory variables, it will not violate the classical assumptions. Remember that point always. Classical assumption is about perfect linear association. That is a situation in which R between x2 and x3 is 1. If it is less than 1, it is not a violation of the classical assumptions. Now, so if collinearity is very high, as it will not violate any of the classical assumptions, classical assumption is only perfect collinearity. High collinearity will not violate any of the classical assumptions. So even if there is high collinearity, OLS estimators are still blue. OLS estimators are still blue. Best linear unbiased estimators is still blue. Now, if this is the case, why we worry too much about multicollinearity? As one econometrician suggests, multicollinearity violates none of the classical assumptions. OLS estimators are unbiased. OLS estimators are consistent. OLS estimators have minimum variance. Their standard errors are correctly estimated. Everything is good. OLS estimators are still blue. Best linear unbiased estimators. So they are minimum variance estimators, unbiased estimators, naturally consistent estimators. The only problem is standard error of the estimator will be a little high. If there is collinearity, standard errors of the estimators will be very high. But you will get the same problem, high standard errors, because we have seen that beta variance of beta hat j is equal to sigma square by sigma x j square into 1 minus r square in the general case. So if r square is very high, correlation between explanatory variables, variance will be very high. You will get the same result if sample size is small. And also the variability of the corresponding explanatory variable is small. So from a theoretical point of view, multicollinearity, small sample size, low variability in X, all are same. From the theoretical point of view, small sample size, low variability in X, multicollinearity, that is correlation between explanatory variables, all are same. Now, to derive or to invite our attention to small sample size, Goldberger coined a term, micronumerosity. Goldberger coined a term, micronumerosity. Now, like a perfect multicollinearity, exact micronumerosity means zero sample size. That is the counterpart of perfect multicollinearity is perfect micronumerosity. And like a high multicollinearity, there is small sample size. So if the sample size is very small, then precise estimation is not possible because standard errors will be high. And if multicollinearity is perfect, no estimation is possible. In the same way, if there is no sample size, estimation is not possible. So at a theoretical level, remember this multicollinearity, small sample size, low variability in X, all have the same effect. So theoretically, all are one and the same thing. Theoretically only, multicollinearity means exact or linear relationship between explanatory variables. But from the theoretical point of view, low variability in X, high collinearity between explanatory variables, small sample size. In terms of effect, they are same. That is why Goldberger introduced the concept of micronumerosity. Exact micronumerosity is the counterpart of exact multicollinearity. And like a high multicollinearity, high micronumerosity make estimation difficult because standard errors will be high. But still, so remember this, multicollinearity violates none of the assumptions. Wireless estimators are still blue. But it is not a consolation in practice. Let us see what are the theoretical consequences. We know that even if there is multicollinearity, what I am talking about is not perfect collinearity, less than perfect collinearity. Wireless estimators are still unbiased. That is true. But we know that unbiasedness is a repeated sample property. It will not say anything about the property of an estimator in a single sample. So unbiasedness by itself is not a very important. Second, it will not destroy minimum variance. It will not destroy minimum variance. Wireless estimators are still minimum variance estimators. Minimum variance means best estimators. And you may have a doubt. While deriving the Gauss-Markov theorem, we have proved that variance of beta 2 hat is less than variance of beta tilde 2. Even if when there is multicollinearity, variance of beta 2 hat increases. Then in which sense we say that it is the minimum variance estimator even if there is high collinearity. The point is minimum variance is a relative property. If there is multicollinearity, variance of the alternative estimator also increases. And when we compare the variance of this with this, variance of beta tilde 2 is still high. That is it. Variance of both estimators will increase. And again, variance of beta 2 hat will be less than variance of beta tilde 2 if there is collinearity, high collinearity. But beta hat 2 is still the minimum variance estimator. Remember this. The third point to be remembered is multicollinearity is a sample phenomenon. Sample phenomenon. Not a phenomena in the that means even if there is no collinearity in the population, there will be collinearity in the sample. As an example, if you regress consumption on income and wealth, there will be high collinearity between income and wealth because as income increases, wealth also increases and vice versa. But it is not necessary that there will be collinearity in the population. And in some cases, you can solve this problem by identifying families with a high income and low wealth, and vice versa. But there are many situations in which identification of such variables will be difficult because we are using observational data not experimental data. So these are the theoretical consequences. So remember this. I mentioned theoretical consequences in the context of perfect collinearity. OLS estimators are indeterminate, standard errors infinite. If it is less than perfect collinearity, estimation is possible. OLS estimators are still blue. From the theoretical point of view, you will get the same issue if there is low variability in X and also if sample size is small. So in the next section, we will see what are the practical consequences. Theoretically, it is not a problem, but there are many practical consequences of multicollinearity, and that is our next concern.